Welcome to this presentation. In this model, I'm going to speak about a space segment. A satellite communication system can be broadly divided into two segments called ground segment and a space segment. The space segment will obviously include the satellites, but it also includes the ground facilities needed to keep the satellites operational. These being referred to as the tracking, telemetry, and command system, that is TT and C facilities. In many networks, it is common practice to employ a ground station solely for the purpose of TT and C. The equipment which are carried aboard the satellite can be classified according to the function. And let us see the equipments one by one. Before that, we'll see the structure of the spacecraft technology. A satellite is basically a self-contained communication system with the ability to receive signals from the Earth and to retransmit those signals back with the use of transponder. A transponder is an integrated receiver and transmitter of radio signals and components of the satellite structure. So what you see here is the structure of the satellite, which consists of an uplink antenna, downlink antenna, and the power segments and command and control systems. So as you see, the signals that are originating from the ground station are transmitted to the satellite, and the satellite receiver which has a receiving antenna will receive the signals from the ground station. Then it is retransmitted to the another destination ground stations. So this is the three-dimensional diagram or picture of the satellite. And the main components of the satellite consist of a communication system, power system, and propulsion system. The communication system includes the antennas and transponders that receive and retransmit the signals. Power system includes the solar panels that provide power. Propulsion system includes the rockets that propel the satellite. The payload refers to the equipment used to provide the service for which the satellite has been launched. The payload is the communication antennas, receivers, and transmitters. Transponder is nothing but on a communication satellite, the equipment which provides the connecting link between the satellite's transmit and receive antennas. The transponders form one of the main sections of the payload, the other being the antenna subsystems. And the bus refers to not only to the vehicle which carries the payload, but also to the various subsystems which provides the power, attitude control, orbit control, thermal control, and command and telemetry functions required to service the payload. Thrusters are nothing but which are fired occasionally to make adjustment in its position. So a satellite has thrusters to fire occasionally. And in communications satellite, the equipment which provides the connecting link between the satellite's transmit and receive antenna is the major component, and that is what is called a transponder. Now let us see the power supply required for an antenna. The primary electrical power for operating the electronic equipment is obtained from solar cells. Individual cells can generate only small amount of power, and therefore arrays of cells in series parallel connections are required. And HS-376 satellite cell has solar cell panels manufactured by Hughes Space and Communication Company, and the spacecraft is 216 centimeter in diameter and 660 centimeter long when fully deployed in orbit. During the launch sequence, the outer cylinder is telescoped over the inner one to reduce the overall length. Only the outer panel generates electrical power during this phase. In geostationary orbit, the telescoped panel is fully extended so that both are exposed to sunlight. At the beginning of life, the panel produces 940 watts DC power, which may drop to 760 watts at the end of 10 years. During eclipse, the power is provided by two nickel-cadmium long-life batteries which will deliver 830 watts. At the end of life, the battery recharge time is less than 60 hours. The HS-376 spacecraft is a spin-stabilized spacecraft. the geographic effect of the spin is used for mechanical orientational stability, and thus the arrays are only partially in sunshine at any given time, which places a limitation on power. Higher powers can be achieved with solar panels arranged in the form of rectangular solar cells. Solar sails must be folded during the launch phase and extended when in geostationary orbit. And huge space communication companies satellite, that is such as 601 satellite, uses the solar sails which are folded on each side, and when fully extended they stretch to 67 feet, that is 20.42 meters from tip to tip. The full complement of solar cells is exposed to the sunlight, and the sails are arranged to rotate to track the sun. So they are capable of greater power output than cylindrical arrays having a comparable number of cells. The HS601 can be designed to provide a DC power from 2 to 6 kilowatts. In comparing the power capacity of cylindrical and solar cell satellites, the crossover point is estimated to be about 2 kilowatts, where the solar cells is more economical than the cylindrical type. So the satellite requires internal power in order to operate various electronic systems and communication systems payload that are present in it. Power system is a virtual subsystem which provides the power required for the satellite, working for the satellite. Mainly the solar cells and rechargeable batteries are used in these systems. The primary electrical power for operating the electronic equipment is obtained from the solar cells. Solar cells produce electrical power from the incident sunlight. Therefore, the solar cells are used primarily in order to provide the power to other subsystems of the satellite. So, individual cells can generate only small amount of power, and the two types of solar arrays are, one is cylindrical and the other one is rectangular solar arrays, right? So, in solar cells, higher powers can be achieved if the solar panels are arranged in rectangular or solar cells. So this diagram shows the solar cell panels for the HS376 satellite manufactured by Hughes Space Communication. And the Earth will eclipse a geostationary satellite twice a year during spring and autumn equinoxes. Daily eclipses start approximately 23 days before and end approximately 23 days after the equinox for both spring and autumn equinox, and can last up to 72 minutes at the actual equinox days. And you can see the graph relating the eclipse period to the day of the year. In order to maintain service during the eclipse, storage batteries must be provided. Usually, nickel cadmium batteries will be used, which the Hughes HS376 also uses nickel cadmium batteries. Nickel hydrogen batteries offer significant improvement in power weight ratio. Thank you.